20 years ago, astronomers weren't even sure rocky planets existed anywhere outside our own solar system. Then we found out they were common. Then we started finding them in the habitable zone, the narrow band around a star where liquid water could survive. And for years after that, one enormous question remained completely unanswered, hanging over every single one of those hopeful discoveries. Even if a rocky planet sits in exactly the right spot, does it actually manage to hold onto an atmosphere long enough for any of that promise to matter? 8 days ago, that question finally got answered. And the answer came from a planet that had already been quietly frustrating and fascinating astronomers in equal measure for the better part of a decade. The planet is called LHS 1140b, a super-Earth orbiting a red dwarf star 48 light-years away in the constellation Cetus. It was first discovered back in 2017, and it has been one of the single most intensively studied exoplanets in the entire search for potentially habitable worlds ever since. Its numbers alone made it a serious candidate. About 5.6 times the mass of Earth, with a radius roughly 1.7 times as large. Figures consistent with a genuinely rocky composition, potentially carrying an ocean, an atmosphere, or both. But being a good candidate isn't the same as being confirmed. For every rocky planet found sitting in a star's habitable zone, there was no reliable way to actually prove it had kept an atmosphere at all. Without one, even a planet parked in the perfect location is just an airless rock, no more likely to support life than our own moon. A team led by Collin Cherubim at Harvard University's Center for Astrophysics set out specifically to close that gap. Cherubim had developed a theoretical model, originally as a graduate student years earlier, predicting a specific, detectable signature that a rocky planet's atmosphere might leave behind. If that atmosphere existed and were slowly, steadily escaping into space. The method had one problem that had nagged at the entire idea since it was first proposed. It had never actually been tested on a real rocky exoplanet before. It existed only on paper, a promising equation with no observational proof behind it. Nobody knew for certain if it would actually work once pointed at a real target, light years away rather than at a chalkboard. In 2024, the team pointed an instrument called WINERED, mounted on the Magellan Clay Telescope at Las Campanas Observatory in Chile, at the LHS 1140 system. That instrument's full name, the Warm Infrared HL Spectrograph to Realize Extreme Dispersion, describes exactly what it's built to do: split incoming starlight into extremely fine detail, fine enough to catch faint chemical signatures that would otherwise be completely invisible. Here's the detail that makes this result far more convincing than it might otherwise be, and the part of the story that turns this from a promising signal into genuinely solid evidence. On the same night, the team caught 2 separate planets transiting their star, passing directly in front of it from our point of view, purely by fortunate timing. One of those planets showed absolutely nothing unusual in its spectrum. The other, LHS 1140b, showed a clear, distinct signature: helium escaping from its upper atmosphere. That contrast matters enormously, and it's the single detail that separates this result from a lot of exoplanet claims that never quite hold up to scrutiny. If the instrument itself had some flaw, or if the signal were some kind of artifact of the observation night, the atmosphere, or the equipment, both planets should have shown the same false signature. Instead, one planet came back completely clean, and the other came back with an unmistakable, specific chemical fingerprint, exactly the kind of controlled, built-in comparison that turns a suspicious blob of data into a real, defensible scientific result nobody can easily wave away. Why helium specifically, instead of something more familiar like oxygen or water vapor? Helium escaping from a planet's upper atmosphere is actually a well-understood, well-studied phenomenon much closer to home. It happens on Earth. It happens on other planets in our own solar system. Researchers already knew precisely what that signature should look like. Driven by a planet's own atmosphere being gently heated and stripped away by high-energy X-ray and ultraviolet radiation streaming from its host star. Finding that exact, familiar signature on a planet 48 light-years away meant researchers weren't looking at something ambiguous or new. They were looking at unmistakable, recognizable physics, just happening around a completely different star. Shreyas Visapragada, an astronomer at Carnegie Science observatories and a co-author on the study, explained the reasoning behind the detection directly. After carefully analyzing the spectra, the team determined that helium was escaping from LHS 1140b's atmosphere, driven by exactly this kind of stellar heating. Cherubim summarized why this specific detail matters so much for the bigger picture. An atmosphere is essential for any planet to support life, as we currently understand it. This is the first time anyone has confirmed one on a rocky planet sitting inside another star's habitable zone. There's an important distinction worth being precise about here. Being located in the habitable zone doesn't automatically mean a planet is actually habitable. It only means the temperature range, in theory, would allow liquid water to exist on the surface, assuming everything else about the planet cooperates. LHS 1140b clearing this specific bar, having an atmosphere that survives, is a necessary condition for habitability, not proof of it. It answers one major question, out of several that still remain completely open. This isn't even the first time LHS 1140b has surprised astronomers. Back in 2024, a separate team using the James Webb Space Telescope proposed that the planet might be entirely ice-covered, similar to Jupiter's moon Europa, or that it could host a liquid ocean beneath a cloudy atmosphere, based on data suggesting it likely wasn't a small, gas-rich mini-Neptune after all. This new result doesn't settle that specific debate, but it does confirm, for the first time with direct evidence, that whatever is happening on the planet's surface, there's a real atmosphere present to study rather than an empty, stripped rock orbiting in a technically promising location. LHS 1140 itself is a quiet, inactive red dwarf, roughly 3 billion years old, orbited by at least 3 known planets, cataloged simply as B, C, and D. The fact that its atmosphere has apparently survived that long, despite billions of years of exposure to stellar radiation, suggests this isn't some fragile, temporary state researchers just happened to catch at the right moment. It's evidence of a genuinely stable, long-term atmosphere, the exact kind of stability that matters most for any serious conversation about long-term habitability. Cherubim framed the significance of this moment against the arc of the entire field. 20 years ago, astronomers were still asking whether Earth-sized rocky planets existed around other stars at all. Then they turned out to be common. Then astronomers started finding them specifically inside habitable zones. Now, for the first time, one of those planets has confirmed it, can actually hold onto the one thing that might make all of that promise mean something. An atmosphere still there after billions of years. The search for a habitable world beyond our own solar system has always been a process of ruling questions out, one at a time, rather than finding one single conclusive answer that settles everything at once. LHS 1140b just ruled out the possibility that it's simply an airless rock. What comes next is already planned. Researchers intend to point the James Webb Space Telescope at the same system, hoping to identify exactly what else might be present in that atmosphere beyond helium alone: water vapor, carbon dioxide, methane, or, in the most ambitious version of that search, molecules that would be genuinely difficult to explain without biology behind them. Whatever else that atmosphere turns out to contain, and whatever the James Webb Space Telescope finds when it eventually takes a closer look. This specific question, one astronomers have been trying to answer for decades, finally has real data behind it instead of just theory. Beyond the visible, beyond what you can see, but never beyond what you can understand. Subscribe and check out the rest of the channel. New episodes on space, physics, and the edges of what we understand, going up every day.